an introduction to graphing the sine and cosine functions. Okay, and we're going to spend, basically what's going to happen is this is going to be, as remember in chapter, I think it's chapter 3 or 4 in college algebra, we did transformations of graphs, right? We're going to revisit that, but we're going to do it with this particular type of graph. Okay, there's 6 graphs that we're going to be interested in: sine, cosine, tangent, secant, cosecant, cotangent. We're going to learn how to graph all 6 of them, but my hope is that I instill in you that if we know what sine and cosine look like, we should be able to generate the other 4 through their reciprocal identities or their quotient identities. Okay. For instance, if I know what sine looks like and I know what cosine looks like, if I divide both of those for the same x value, that should give me a point that is on the tangent function, because sine divided by cosine is tangent, right? So that's kind of the goal as we move forward. We're going to move these things up and down. We're going to stretch them. We're going to shrink them. We're going to stretch and shrink vertically. We'll also stretch and shrink horizontally, which is something that we have not talked about in great detail because of the nature of the polynomial graphs. It's kind of hard to realize whether a horizontal shift has been, or a horizontal stretch has taken place visually, but it'll be really easy on these types of functions. Okay, the types of functions that we're talking about right here, any trigonometric function is referred to as a periodic function. Okay, and periodic just simply means that it repeats itself over and over and over and over again. Okay, and if it repeats itself over and over and over again, there is a defined distance of that repetition, or for that repetition. Okay, and what I mean by that, and we call that defined distance the period. Okay, and here you see it described as one point on the graph to the next same point. That's fine. I think that's how our textbook describes it. I like to think about it as the distance it takes for the graph to begin repeating itself. Okay. So if I look at, we're just going to take one function here. Let me change obviously I like Desmos, but GeoGebra for graphing periodic functions is my go-to thing, because I can change the x-axis in terms of pi. Okay, so I can do something like that Desmos doesn't allow me to do. Okay, so every major vertical grid line here is now a multiple of pi over 6. Okay, and if you think about it, okay, this is pi over 6. Add pi over 6 to that, you get pi over 3. Add pi over 6 to that, you get pi over 2. Add pi over 6, you get 2 pi over 3. Is this the unit circle laid out in a straight line? Okay. Now, I don't have my pi over 4s in there, but if I go x equals pi over 4 times k, let's let k be a slider here between -5, let it be 1. And if I trace this, okay, all of those lines would be the pi over 4s. That kind of makes sense? And you can see that the pi over 4 is halfway between pi over 6 and pi over 3, because they're 45 degrees is 15 degrees from 30 and 15 degrees from 60. Okay, so that's that relationship there. The only thing I wish I could do is tell GeoGebra to put my pi over 4s in here as well. I can't. The only thing I can do is ask it to write it in pi over 12, terms of pi over 12, and then that would give me all my pi over 6s, all my pi over 3s, and all my pi over 4s, right? Okay. So that would be something that we do later on. But the reason we do that is because when we graph the sine function, the cosine function, we're actually, and we talked about this, I think last Thursday, or Friday, we're taking the theta, comma, the y value off the unit circle, okay? And that is going to give me the sine, okay? And I'll write this down again in more detail tomorrow. But that's the sine. If this was an x value that we're using off the unit circle, then we would create the cosine, okay? But the sine function is that graph right there, let me zoom out. Would you guys agree that it repeats itself in the same behavior over and over again? Okay. If we look at, I'm just going to go, if we're looking between 0 and 2 pi to show me the sine function. Okay, let me get rid of this gray one. Okay, so if I look at that sine function right there, would you guys agree that this point right here looks a lot like that point right there? Okay, and really right now those are the only 2 points that are the same. Okay, and actually I think I want to make this, I think I can do it this way. Good. Okay, so let me put a point on here. So x of a, comma y of a. So if I do that, obviously it's going to just put the same point. So this is how I just get GeoGebra to pull out the ordered pair, or the coordinates of this ordered pair. X of a, we'll say whatever this a values, or a point's x value is, capture it, comma whatever that point's y value is, capture it. So if I hit enter here, it's just going to put a point on top of a. Does that make sense? Okay. But I want to do this. I'm going to take the x value here, and I'm going to add 2 pi to it. Okay. I'm going to leave the y value of a the same. Okay. So I'm just going to do that, and I get that point b. And now what this allows me to do is, as I move a, you see that it moves b kind of the same way, right? So my initial question was, if I look at point a, is that exactly the same as point B? Okay, but as I move it to the right, okay, it starts to change point B. I'm going to trace point B. As I move A, tracing point B, does that produce the exact same curve a second time? Okay, so that first green section is referred to as one period, and sometimes you'll hear me say one cycle, of the sine function. And it's analogous to one revolution around the unit circle. Okay, it's the same as one revolution around the unit circle. The black one is a second period of that curve, and it would be analogous to a second revolution around the unit circle. And we could keep doing that as many times as we need. Okay, and as I keep moving A along this, now the black curve, it's going to repeat B over here. And eventually, that would get me that curve right there. Does that kind of make sense? Okay, Keaton? That was putting in my, I deleted it, but that was putting in the pi over 4 increments. But that is my sine function. Okay, and that demonstration there is showing you the period. Now, the period, so if I go back to sine of x, the period is the distance it takes for us to realize that the graph is repeated. Okay, so basically the idea is, if the way I set this up is that A and B right now, that distance would be where they're repeating. I could put a point anywhere on here. Okay, let's say I put that point right there. C is that maximum. Okay, and I go through and basically just try to figure out, where do I come back to that position? It'd be right there, correct? Okay, the distance between those 2 points, C and D, should be the same as the distance between A and B. Okay? And those distances are both 6.2832. What number is that? That's 2 pi. Okay? So and this is for the parent function of the sine curve, the period the period is 2 pi. Okay. Now that changes as we change our function. So we talked about this being periodic. It means it behaves in that replicating or repeating behavior. If I take my sine function and I'm going to adjust this x value. If you guys remember when we were working with like x squared and x cubed, if we multiplied the x by a coefficient before squaring or before cubing or square rooting or whatever the function may have been, it is going to create a change in it's going to change the horizontal shape. Okay, so what I'm going to do, I don't know if that, yeah, I don't have that one highlighted. Okay. So you see now, so the sine function, I've got 2 on top of them. I'm going to leave the green one alone, and then I've got this gray one. The gray one is now changing that green curve by compressing, squeezing it down. Does that make sense? And basically what happens when I change that is now the period of that gray one would be from this point here to that point there. Does that make sense? Okay, whatever that distance may be. Some people like to look at 0, 0 being the point that they look at and then say, okay, where do I come back to the x-axis in the same behavior? Here I come back to the x-axis, but I'm decreasing here. Okay, so I'm going to come back here. Now I'm increasing through the x-axis, so that point and that point relate to one another. And we find that distance. But that distance will be the same as the distance between those two. Does that make sense? But what happens there is, see if we can find that distance. We'll do it this way. Customize toolbar. If we look at the distance between G and C now, that distance is 1.257. 1.257, which, if I think about 1.257, or think about that number, what we can do is take 2 pi, and we divide it by k, which was this 5 right here. I'm going to hit enter, and I get that same number that it's showing as the distance between those. Does that make sense? As I move this slider, that number changes to this quotient because it's called G. We want G to I, not G to C. We're going to get the same relationship. So G to I, 1.57. Now you see if I go back to 5, still that 1.2566 number. Going K is 3, so spread that out, and now I get 2.094, which is what it's saying it should be. We'll go all the way down to K being 1, and now we go back to 6.28. Now it's not showing it for some reason, but I don't even know where that point went. Yeah, there we go. Thank you. So looking at those, we still get G to I, which would be these two, which would be analogous to between those two, still be to 2 pi. Does that kind of make sense? Okay. So the way we can change, I tell you that the period is 2 pi for the sine function, but we can change it. Okay. The parent function sine of theta or sine of x is 2 pi, but sine of 2x now is that period is now just pi. Okay, because we take 2 pi and divide it by that coefficient of your x value to determine the period. It was not a big deal right now. We'll get into doing more of that later on. But that's what a period is. It's the amount of time that it takes to repeat itself. Okay, so are there, everybody? All right. The next term that we want to talk about is amplitude. Okay, so give you a minute to write down the amplitude. It's the highest and lowest value that a function can reach. Okay, and that's maybe not the best way of stating it. Okay, because when we shift this thing off of the x-axis, it gets a little bit murkier. Okay, so you write that down, but we're going to use this formula here to explain this concept a little bit better. So I'll give you a minute to write that down. All right, so when we talk about the sine function and just the parent function, that's all I want to look at right here. Let me get rid of all of that and just put the normal one back in, sine of x. Okay. The amplitude, okay, is the distance that we can realize from, I'm going to call it you're going to hear me call it two things, the transverse axes or the wave axes, or I think I wrote it on the notes as axis of wave, or several different ways of visualizing it or actually articulating it. But it is simply that distance right there, okay, which is going to be the same as that distance right there. Okay, so it's when it says the highest or lowest that the wave can reach, ultimately that's accurate for just the sine function when I don't move it up or down. It is the distance that the maximum is away from that axis right there. We call that the wave axis or the axis of wave, transverse axis, which is basically the horizontal line that cuts our wave in half. Does that make sense? Into a top half and a bottom half. The distance from that axis to a maximum or minimum is what we refer to as our amplitude. Okay. Now our amplitude, another way of determining it, I had a formula there that said it was the absolute value. Now I put max minus min divided by 2, but it doesn't matter the order since we're taking the absolute value. So I'm sure write m minus lowercase m, capital M minus lowercase m, divided by 2. It's the average of those. So if this maximum here, if capital M is 1 and lowercase m is -1, those are the y values, right? Those are the maximum minimum values. If I subtract those, 1 minus -1, what's 1 minus -1? 2. What's 2 divided by 2? 1, right? Absolute value of that is 1. So that thing right there is a distance of 1. That's the amplitude of our sine function. Does that make sense? Okay. What I want to make sure that we don't do is say that our amplitude is that distance. So, okay, everybody? It's always essentially half of that distance. Okay. The axis of wave can be found by identifying the midpoint of that distance. Okay, so if this distance is 1, that's -1, that's a distance of 2, right? Okay. If I add those together, so this is how we find midpoints. We take the endpoints and add them together, divide by 2, right? So take 1 plus -1 divided by 2. Well, that's 0 divided by 2. It gives me 0, right? The axis of wave is y equals 0. Okay. Now, all of that can change and does change quite a bit for us when I do something like this. Let's say I'm going to put a 2 there, put a 3 there. I want to add 4 there. And I get that graph now. Okay. Now I've stretched it. Think about this. A number out in front of a function always is a vertical stretch, right? That 2 out in front was a vertical stretch. That 3 that's being applied to the x, okay, when I multiply x by something, if that something is bigger than 1, it's actually a horizontal compression, okay, before I apply the sine function. So that's why that we've got more oscillations or cycles of this graph. Than what we did with the sine function. And then I add 4 to that. You see how that plus 4 took the point that was, so if I compare these things, okay, so that purple one's the sine function, that's the parent function. That plus 4 took that point right there and moved it right there. Does that make sense? Okay. Basically, it took my maximum and it also moved my maximum up. Okay. Now there's some other things that happen here. So it's not a direct up 4 with that maximum. But basically what happens here is we had in this one an axis of wave that was at 0. Now here, if I put y equals 4 in, that's my axis of wave. Does that make sense? And it's all because of vertical translations. Okay. Now, how can I find that axis? If I didn't know that, if I didn't realize that with transformations, I could find that axis of wave by taking that value right there, that maximum value, which is 6, that minimum value, which is 2. If I add them together, I get 8. Divide by 2, you get 4. Okay? Now, once I have that, there's a couple different ways you can do this. If that's 4, then what is that distance right there? That distance is 2, which is my amplitude, right? Okay. Could I have found that also by taking 6 minus 2 over 2? Does that still give me 2? Okay. That 2 right there, that is the amplitude, is that number right there in the algebra portion of the definition, okay, for the function. I mean, we talked about this a couple days ago. We talked about AM radio, FM radio, okay? And there's all kinds of signals, and there's signals that are bouncing off of you right now. There are AM and FM radio signals bouncing off your body right now, okay? But nobody can hear the radio right now because your body doesn't have a receiver to decipher the messages in those waves, okay? Basically what happens is if I'm the radio station and I code a message in this blue wave, okay, and I encode it based off the amplitude, then you need to be on AM radio because that stands for amplitude modulation. And when you take the tuner and change it on the radio to 1150, you are now trying to match a radio signal that has an amplitude of 1150. Does that make sense? Okay. FM stands for frequency modulation. Frequency it's related to the period. It's basically how many waves pass through a distance in a specific time. Okay. You guys talk about waves yet in physics? I know I've asked this like almost every day. Still not? Okay. You'll talk about frequency in physics, and what happens then in frequency is that it's that idea right there. Does that make sense? Okay. So I'm now changing essentially the period and how many oscillations occur of the sine wave between a certain time interval. Okay. That is FM radio, frequency modulation, that we encode those types of signals. So my receiver on my radio would be able to decode that message. If you've ever done anything with your computer, you get into the computer and you look at your Bluetooth network card and all that kind of stuff. There's always a hertz, an HZ, or a gigahertz, GHz. Okay, hertz is the unit that we use for frequency. Okay, and basically talks about how compressed or elongated, stretched out those waves are. Anything that you ever deal with radio-wise is working using these things. Okay, we'll pick up with that tomorrow. No new homework. Make sure you're still working on the current homeworks. See ya.